Hello, everyone, and welcome back. We are still talking about related rates, and last lesson we talked about notation, and this lesson we're going to start to look at applications of it, problems that include related rates. In this lesson, it's all about related rates where Pythagorean theorem is at play. Now, we're going to look at two examples, and what's important with related rates is two things. One, always draw a picture first, and then two is understand the geometry that's at play. Okay. And then with these two things, using calculus, we can understand these related rates and make good sense of how things are changing relative to other things changing. So here's the first problem. A hot air balloon is rising off the ground. A crew member is standing 300 feet away with a 100-foot rope, releasing the rope slowly as the balloon rises. If the crew member is releasing rope at 2 feet per second, what is the rate at which the balloon's height is changing when it's 50 feet off the ground? Okay, so let's draw a picture of this first. So we have a hot air balloon that's rising vertically. And there's a crew member that is, what's it say, 300 feet away. So notice right away that when we make this picture, so this is the rope, is that we get a right triangle in which Pythagorean theorem is going to help us. So I could maybe call this even, call this height for h, call this the r for the length of the rope, and we'll call this d for the distance the crew member's away from. So someone's standing right there. Okay? Now the relationship right away that we would know is that we would know by Pythagorean's theorem that d squared plus h squared is going to equal r squared. Okay. Now, since we're talking about how things are changing, now what we want to know here is if we fill in the numbers, is that he's standing 300 feet away, so we know that this is 300 feet, a 100-foot rope, and he's releasing it slowly. If the crew member is releasing rope at 2 feet per second, so as he releases the rope, we know that dr dt, the rate at which the rope is being released relative to time, is 2. And the rate at which the balloon's height is, we want to know what is the rate at which the balloon's height is changing. So basically what's asking is what's dh dt when it is 50 feet off the ground. So that's the big question here, is what's dh dt when the height is 50? That's what we're trying to solve in this problem, okay? Now, we don't have to do Pythagorean theorem here. We already have the lengths of the three sides, so let's look at the rates. Now, how are we going to talk about the rates of this function is we have to take the derivative of it. And we're going to use our technique of implicit differentiation. Now, this is where it matters with what are we analyzing the change relative to, or relative to. We're talking about how is the height changing, and we're talking about how it's the releasing rope as it's changing per second. So it's per time. So we're going to take the derivative of this function relative to time, t. Okay. How is all of this changing as time changes, infinitesimally small moments? We're going to study that. So before I even plug in numbers, I just want to look at this right here. So if we take the derivative of this, implicitly, it's going to be the derivative of the outside, leaving the inside alone, and then times the derivative of the inside. Well, again, notice implicitly that we're studying how is the distance changing relative to time. Well, we don't know, so we have to write dd dt. Plus, the derivative of h squared is going to be chain rule, derivative of the outside, leaving the inside alone, where you'd leave the h, times the derivative of the inside. Well, what's the derivative of height relative to time? Again, we don't know. Now, notice what's different than last chapter is now we have two derivatives or rates in our equation that are studying how two different things are changing relative to time, which that's why we're talking about related rates. It's multiple things changing as one thing changes. It's equal to, and we're not even done yet, this would technically be 2r dr dt. Okay? Now, if we plug in what we know before we even do any of this, so now that if we were to plug in equations, we would have had 300 squared. Well, we can actually plug in here. D is 300, so it'd be 2 times 300. Now, what was the rate at which the distance was moving? Now, he was not moving at all. So this is actually 0. This is going to go away. He was standing at one spot. This was not changing. Plus 2, and then the height was 50. And then we don't know dh dt, so again, that we'll just write. equal to 2, and the length of the rope is 100, and it's saying that he was releasing the rope at 2 feet per second. So we would get there that dH dt is going to equal 2 times 100 times 2 all over 2 times 50. If you divide that over, in which that's going to end up becoming, that would be 1 and that would be 2, 4. So that means that the balloon's height is changing at 4 feet per second when the balloon is 50 feet off the ground. And that was us using related rates to solve this. Okay. Now, I know that this might have caused some concern. Maybe you're like, why was that 0? Well, what if we would have plugged in numbers earlier? What if? So we would have said 300 squared plus 50 squared equals 100 squared. When you take the derivative of this relative to time, I guess the similar situation comes up, is 300 squared, the distance. Well, how is that changing as time is changing? It's the same idea that that's just going to go to 0. Plus, and then it would have been 2 times 50 times dH dt plus 2 times 100 dr dt as the rope was changing. You can see that they're all kind of related in that sense. It makes sense that this is positive, by the way. It makes sense that dH dt is positive because the balloon is rising, because the height is increasing as time increases. So it makes sense that it is positive there. But that's using related rates with Pythagorean's theorem. Let's look at one more example, and hopefully this clears it up. So something a little bit different. A police car is approaching a right-angled intersection from the north, chasing a truck heading east. When the police car is 6 miles north of the intersection, the truck is 8 miles east of the intersection. With radar, the police determine the distance between them is increasing at 20 miles an hour. If the cop car is traveling 60 miles an hour, what was the speed of the truck at that moment? So again, draw a picture first. So we have a police car is approaching a right-angled intersection from the north. So from the north, it's approaching a right-angled intersection. And then another car is heading east. So this is a right angle, and that car is heading east. Now I'll put a point right there. So here's the cop car. Here's the truck. Okay, and we have a right triangle here that we can study. And what do we know in this problem? So we might call this, say, x, y, and the distance between them, I'll call d. Okay. Now, what do we know? When the police car is 6 miles north, so we know that x is 6, the truck is 8 miles east, and with radar, the police determine the distance between them is increasing at 20 miles an hour. So the distance between them, again, this is the distance between them, d, is increasing. So again, that's your rate. So what we know is that the dt relative to time is equal to 20. If the cop car is traveling 60 miles an hour, so the cop car, dx dt, is equal to 60, and it's actually going to be negative 60 here because we're heading downwards. What was the speed of the truck? So in other words, what we want to know is what's dy dt when at that particular moment. So when x equals 6, y equals 8, etc. Okay? So using Pythagorean theorem, we would say that x squared plus y squared is equal to d squared. We're going to take the derivative of this relative to time again. How is all of this changing as time changes? Implicitly, we're going to end up getting 2x dx dt plus 2y dy dt is equal to 2d d dt. Okay, now plugging in what we know, we would have 2 times 6, and that's traveling at negative 60 miles an hour, plus 2 times 8, and we don't know dy dt, that's what we're trying to solve here, right? This was what is dy dt at x equals 6. And is equal to 2. Now, what's d? Now, because it's Pythagorean theorem, we could solve for this. So, side note, we would have done 6 squared plus 8 squared equals d squared. I already kind of see that's going to be a 3, 4, 5 triangle, because if you divide each of these by 2, you'd see it's 3, 4, and it would have been 5. So I know it's going to be 10, but working out, you'd see 36 plus 64, 100, which implies d equals 10 by square rooting both sides. So that's 10. And the rate at which the distance is increasing is 20, okay? So solving for dy dt now, we'd have dy dt is going to equal 2 times 10 times 20 minus 2 times 6 times negative 60 divided by 2 times 8. So I know you can multiply it out, but I'm just working with what I got there. And then before I even use my calculator, see what I can get rid of. The 2's you can get rid of. I can divide this by 2, making that a 4. That would make that a 5. That would make that a 3. And then I would end up having 100 plus 180 divided by 4, which gives me 280 divided by 4, which actually gives me 70. So that tells me that dy dt, the rate at which the truck was moving, was 70 miles per hour, when x was equal to 6. And there you go. So that's looking at related rates a little bit, okay? And I hope that makes sense to you and how we work with related rates, because it's the idea that now when we take the derivative with respect to, we have to be cognizant of what we're studying change relative to. We're studying change relative to time, but when you take the derivative implicitly, what are we going to be left with algebraically, equation-wise? And then plug in what you know, and hopefully that helps you go from there. Hope that makes sense, and I hope you can figure out that lesson and that problem for you with the ladder falling down a wall. That's a pretty classic problem. All right, bye-bye.